All right, hello everybody, and thank you for inviting me to this year's Australian Accessibility Conference again. And although the circumstances are a bit different in the way I will present things, I'm still excited to give you an account of my journey in this very kind of unique year of 2020. And hopefully, we're going to have a good transition into 2021. But So the topic of my talk is going to be a bit of a report, a debrief on what has happened to me since I last spoke at last year's conference. So just a quick recap, I was actually going on a world tour, starting from Australia to meet multiple experts in different fields in astronomy to actually go through a Q&A within their expertise. And I've actually studied their field, just kind of digesting all of their papers, figuring out what are some of the components or parameters I needed to understand so that I can actually include it into my project, which is Astrios, which is a astronomy app using augmented reality and which kind of pulls data from all sorts of different data centers across the world, including NASA, ESA, multiple agencies. So the journey started after I left in Perth. The journey started with South Africa. I did a quick stop in St. Denis in Reunion Island, just for a quick, brief kind of holiday. Then I went to South Africa, and immediately I was, both feet, I guess, in the mud by meeting with the IUD team, which is the South African astronomy group, which has a whole bunch of projects which are sponsored by the UN, which allows people in developed countries to actually, uh, you know, uh, get involved, I guess, in the science, in the field of astronomy, as well as in the human curiosity, which is to look up at the sky and figure out what's happening there. That was quite interesting. We did a podcast for that, and probably I will send you a link for all the different episodes that I've produced since then. The next stop after that was to go to Egypt in Cairo, and essentially, kind of trace back the history of the relationship between humans and the sky via those structures, which are ancient, very, very ancient and formidable, which exist all across Egypt. Some of them are still under the sand, some of it have been unearthed, and obviously the most famous one is the three large pyramids on the Giza plateau. So what I did there is to kind of investigate some of the mathematical truths across all of these buildings, how they were built, who built them, what were the astronomical objectives for which those buildings were actually built, and found some quite some interesting knowledge from it. And I interviewed a French um, Egyptologist who usually focuses on just the history and the culture, but astronomy is really, really deep in the culture of ancient Egypt. So that was another project. Then I moved on to Israel, where I met with some physicists at the University of Technion, Faculty of Physics, which actually has been established by Albert Einstein's associate, Nathan Rosen. And we did another podcast over there, and I also kind of, I guess, got immersed in the culture in Israel, the Jewish culture, the Hebrew culture, which is absolutely fascinating. From that point, I went to Kurdistan for another podcast. Unfortunately, we actually had the lockdown. All the countries started to shut down one after the other. And my return route was actually closed off. So we had to really kind of, rush to try to get a different route to get back home to Australia. And we were lucky enough to actually find a different route through Dubai and came back home. So initially, had a couple more countries to go through and a couple more experts to meet. But the lockdown and COVID-19 has actually kind of rained on that parade. However, I continued with my research and investigation and have different other episodes that I've actually produced with different experts across Australia and the world. Some interesting ones are with Seth Shostak from the SETI Institute, which is the search for extraterrestrial intelligence. We had a very interesting conversation about, what techniques we're currently using to listen to the sky. We demystified some of the romanticisms that we can get in terms of what is the meaning of listening to the sky, which actually is very, very boring, to be honest, because an event such as finding an intelligent signal has never occurred so far. So the probability of that happening in the future is still very, very slight. Although the probability is non-zero, it is very slight, and it would be very boring to just listen to a portion of the sky forever. However, so in parallel with this, I continued with my development and research in trying to sonify the data that comes from the sky. So this, I chained it together with some courses I have taken at UQ, at the University of Queensland. Just as an aside, I've really decided to focus to artificial intelligence and machine learning, because those are fascinating fields in computer sciences. It's really, those are fields which are really in ebullition, and the value and the power of these algorithms and techniques just kind of span across multiple sectors. The one that interests me is actually digital signal processing, so audio or photometric signal processing. So I'll show you some of the what I've actually understood was possible to do by using sonification. And this has to do with, some of the questions we pose ourselves as blind people. Well, how can I access graphs? How can I try to visualize what a graph is, what a histogram is, what a distribution looks like, a Gaussian distribution looks like, and so on and so forth. So on one of the assignments, what I've done is actually apply sonification to try to understand graphs. And this was actually produced in order for me to move forward with capturing the signals that come from the stars, exoplanets, galaxies, black holes, etc., and to sonify it so that we could try to maybe unveil a bit more of the mysteries that come from the sky using sound. So I'll share this.
Stop. Share. Find.
Okay.
Application. Zoom.us. Zoom share toolbar window. Mute. Zoom.us has new system dialog.
Okay. I'm sorry for the cacophony of the screen reader. It'd be great if we could telepathically do that, with the Neuralink system coming from Mr. Elon Musk. Hey, Elon.
Zoom.us.
Shout out to you, although you probably never hear me.
Safari. Mail. Column view one item selected. Cycle through windows. Gaussian. Column view one item selected. Gaussian.
Okay, I got it. So here, I will make you listen to something which in the sciences and in statistics and biological sciences, population, or even star formation, we use this thing which, a term which is called Gaussian distribution or normal distribution, which is kind of a scientific way to see, how different a sample set of things or objects in the world sampled at large quantities have this kind of distribution, which is like a bell-shaped distribution. And most of the times we want to know if this distribution is actually bell-shaped because then we can understand that we can sort of kind of pull out some more information about it and see if we can extract what is called correlations. What one kind of entity in the world would relate to another entity, or inversely relate to that entity, or if they have absolutely no correlation, that means they're independent from each other. So this Gaussian distribution, which is normally a bell curve, if it actually does not sound like a bell curve, it would just have a ascending or descending kind of sound. And so what I did is I created a stereo signal processing script in order to understand if a distribution is Gaussian or not.
Column view 1 item selected. In column, Gaussian matrix size 16x16.mp3.
Okay, so
Gaussian.
So
X left sample right dot mp3. BX left sample right dot m. BX.
So this basically was just an ascending kind of sound. And on the left-hand side was the sample that I took from the data. And the right-hand side was a generated normal distribution. So what you can do is you can figure out whether the data set that you have is following through with a normal distribution by comparison.
X versus sample. CX left, DX left sample right dot m. X left sample right dot mp3.
I'll make you listen to another
FX.
So here, it was actually not a Gaussian distribution. If you heard the dip at the beginning, it just kind of went down like a J shape. So like the character J, and then went back up. And this would not be a normal distribution. So you can sort of pull information out of that and then, make out what you want to, by using some other tools to further investigate what is happening with that data. So another way to understand data better is to use histograms. Histograms are kind of a way of segmenting a whole bunch of data points into kind of candles, or let's say vertical bars. And the height of that vertical bar would tell you what is the maximum value of that segment. So for instance, a histogram can also tell you if a distribution is Gaussian, or if it goes descending or ascending. That means there's a bit of an offset. That means there's a larger proportion of data points. Let's say, for pure example, in a population, human population, normally you'd have a bell curve shape. But in the histogram, if you don't have a bell curve shape, that means you kind of have a strange population, because maybe, there's a whole bunch of people who are very, very short, and there's a very small amount of people who are tall. That doesn't actually occur in nature, or in human population, or in many other things. For example, in flower lengths, in fruit sizes, and also in star sizes in the context of my research. So I will make you listen to
Max histograms.
A histogram.
A histogram.mp3. B C histogram.
So here it started low, went slightly up, and then went all the way down. So it's not exactly a Gaussian distribution. Here the sound going from left to right, it kind of curves up and back down. So all of the different histograms are actually quite Gaussian. So that's a good thing. This is absolutely not Gaussian because it's got a J shape. And so the right-hand side, the larger values are way more, there's much more weight on the larger size than on the smaller size. And the midsection, which is normally the mean or the average, is very, very low. So this is not a Gaussian distribution. However, there's some interesting properties that you can extract from it. Now, after this, there's another thing that is important in astronomy, which is photometry. So that's kind of raw light data that you would get from different sections of the sky. And sometimes what you would want to do is to figure out what is the general luminosity of a region in the sky so that you can sort of, figure out whether it's going through the infrared spectrum, whether it's going through the photometric spectrum or UV or even gamma. So UV and gamma are the kind of things that when it bursts, and even if you're, let's say there's a gamma ray that bursts, that would burst on the sun, God forbid, we would fry instantly. That's how high the frequency and how powerful that signal actually is. So that is something in conjunction with something else, which is basically chaos. It exists all across the sky. And so you need to be able to make something out of that chaos, understand what is happening. And normally scientists do that visually in a 2D space. So, horizontal and vertical. And in the case of being blind, well, how do you do that? Well, here is something.
Cycle through windows. Gaussian. Gaussian.
Okay. Now, this is a bit of a, how should we say? It's not music. It's not, your favorite pop song or blues or jazz song or rock song. It's purely scientific. So please bear with me. It's actually an acquired skill. But I have actually validated this with my coordinator, as well as some tutors. And I've compared, so listening to the sound of the image, which is scanned top left to bottom right, or stacked meaning that every pixel from top to bottom vertically are played at the same time, but with the stereo spanning swiping from left to right, okay? So here, what I will do is I will make you listen to a Gaussian 2D. So it's the same normal distribution I spoke about earlier, but this time it's in the 2D case. So this is, I will do the stacked one.
Coles Jackson, Gaussian. Gaussian matrix size 16x16.mp3. Gaussian matrix.
And you can modulate this to have multiple different types of resolutions. So you can have smaller resolutions, which are kind of very blurry, low resolution ways of listening to what is overall happening on a 2D image. Or you can increase the resolution to actually have a bit more of a fine grained understanding of what is happening.
Gaussian matrix size 40x40.mp3.
So here.
Function is Gaussian matrix size 40x 40 rows are stacked.
So this kind of says that towards the outside, the brightness is higher, and on the inside, the brightness is actually lower. But because this is stacked, this technique does not give you enough information about this. So what you can do is instead scan the image. So here's the same one, and just to remind you, this is black and white.
Function is Gaussian matrix size 40x 40, scanning top left to bottom right.
So like I said, this actually scans the image from top left to bottom right. And you can hear clearly that towards the middle of the actual audio sequence, the values were going up. So that means there's kind of like a spherical, blurry bubble shape in the middle. And this will tell you, well, this is actually a spot where there's kind of a emanating light, okay? Now this is simply for black and white, but you can do this also for color. And here, as an example, I will give you the Mandelbrot set, so which is a famous set. It's a fractal, what we call a recursive function. So it's something that goes and recurses on itself. Maybe some of you know about the Fibonacci sequence. It is kind of similar, except that this kind of represents the relationship between order and chaos.
Mandelbrot matrix size 13x15.mp. Mandelbrot matrix size 52x60.mp3.
Okay, here I've added R, G, and B values.
Function is
Mandel
Mandel
Rock-
matrix size 52x60. Scanning top left to bottom right. Red, green, blue.
So this is rather low resolution. However, the image is represented by different bubbles, and there are two dark spots in the middle from which emanate different colors that are coming out, and the dominant color is actually blue. So this is what I actually explained to my tutor, and he said, this is exactly it. So if this is kind of the first time you listen to it, it might sound strange. It might sound just like some extraterrestrial speaking to you, but it's actually not. It's actually valid scientific data that you can interpret by using sound. And obviously you can add some descriptions and, various things and information that would help you, understand it better, such as, maximum values, minimum values, and so on and so forth. So the idea about all of this is comes kind of hand to hand with so a group which is called the World Sonification Leadership Group, which includes multiple teams across the world, all working on the same thing, which is to standardize sonification for the sciences. And this includes the NASA Master Archive Group. It includes a group from Monash University, also from the UK. There's also some people from Canada, as well as in the west coast of the US, and a couple of teams over here in Brisbane, including SonoKids. They're doing sonification for education for kids, for early age sonification for blind kids, and use sound in order for them to actually understand the world a bit better. And there are different levels, we're different teams, and we're all collaborating to try to find an actual standard to represent the information which is normally visual to something which is visual plus sound. And so the whole point of me doing all of this research is in order for me to allow users to actually analyze the data that comes from exoplanets. And if some of you have been here in the last year's talk, I actually made you listen to what is called a light curve, which is the information coming from those exoplanets or stars, which potentially may have exoplanets, and made you listen to an example where there is an actual transit of an exoplanet. So what I would like to do is to integrate all these sonification tools into the app itself, which is Astrios. Unfortunately, the Zoom is not doesn't have the option to allow me to share my iOS device for me to give you a live demonstration. However, I have some videos that I can show you.
Cycle through windows. Screen grabs. Column view one item selected. Video 26419. Video 26419. 220. Video tutorial. Constellation.mp4.
So here is the video of a constellation.
F2. Console.
Aurora Borealis. Bootis.
So I'm pointing my
Magnifying.
phone around, and I found Bootis in the sky. I magnify. And here you can listen to the chimes of each of the stars.
Minor mode.
To a specific frequency. And you have multiple modes. So you got the major stars, minor stars, and you got the exoplanets. So the exoplanets actually come from
Exoplanet mode,
which is called TESS. And TESS is currently in the sky looking out into the universe and giving us a whole bunch of star systems which are potential candidates for exoplanet transits. So the next feature,
resigning,
Astrios, is actually going to
Screen grabs.
allow the user to look for these exoplanets, tap on all of the candidates which exist, and to start analyzing the exoplanet in multiple different ways. So all of those tools that I've shown you, it will have the ability to just take the raw information and map it to a sound as well as visualize it, because what you want to do as a user, as a blind user, is to collaborate with a sighted user in order for both of you to be able to play the same game, which is to hunt for exoplanets.
Tutorial part 1.mp4.
And so the app itself is augmented reality, it's science, it's a conjunction, let's say, of design, accessibility, science, and interactivity. This is how I like to put it, because I find it really important to gamify something which is normally kind of, it has quite a high access level, threshold, and learning curve. So to simplify it so that it's actually gamified, but also to provide all of the accuracy and the scientific data in order for those who want to go a bit more advanced, in order for them to be able to play with this. So here,
The Celestial Search Telemetry, or CST, system allows you to search for all known and confirmed bodies by using a two-finger swipe up. Go ahead.
so
Querying.
swipe up.
The CST is divided in two sections. Touch and drag on the right side to switch objects to search. Go ahead. Constellation. Tap on objects on the left side to select. Please now look for the Auriga constellation. Loaded. Auriga.
And now you can track Auriga in the sky with your phone.
Perfect. Flawless. We are now in the Auriga system at a distance of approximately 74 parsecs. Please drag your finger around to orbit the system.
And this actually works in surround. If some of you have the new AirPod Pros,
Optimal.
you will have...
As you can hear, the
surround.
stars are emitting variable chimes. The higher the tone, the earlier the star. Metallic chimes are older celestial objects. To turn on geostatic orbit and feel the stars, please swipe two fingers left or right on the screen. Geostationary.
Geostationary is when you freeze the image.
Mencalina 4 left.
The stars.
Capella 3 left. Oidis 2 left. Hyades 1 left. Use two finger swipe up to bring the system details into view.
So you got the up-to-date detail
Perfect.
of the constellation.
When you've taken notes, double tap on the sides.
And every image is also sonified, so as you touch the
Now tap once on the side. You have 3 filter modes. Now to double tap on the side. Minor, mode, double tap again. Exoplanet, mode. The exoplanet mode shows up-to-date discovered planets around host systems. Feel around for an exoplanet if you can't see through the dark clouds.
Screen grabs.
So this is so far the progress of my research. I will be adding a visual and sonified plus haptic graph system, which I've actually coded during my uni time, and it's actually a very nice graph because it's just as valid for scientists as for blind users. It will have single graph, multi-line or multi-line stacked graph lines, histograms, and as well as photometry for all of the spectral categories, so the entire spectrum of light. Basically, it's the entire spectrum of signal, so it goes from infrared all the way to gamma ray. And you can actually scrub it with your finger, analyze the data. It's not just static audio as I've played earlier in my demonstration, but this will all be interactive in 3 ways, so visual, sound, and haptics, so that this can actually work for everybody, including those who are completely blind, like myself, and those who are sighted, because I have some sighted friends with whom I like to go out camping, looking up at the stars, discussing about them, pulling up the details about each of these objects, figuring out if there are any kind of interesting events happening, such as coming up on the 21st of December. That's when Jupiter and Saturn will be the closest in the sky, less than a degree in the sky. So that's quite an event. And we can sort of all enjoy that at the same time and pull out some information, educate each other, and see if there's some interesting sounds that we can listen to and analyze. So this is so far my journey. It will continue on 2021 with hopefully if the lockdown kind of eases in Europe, US, and Canada, but I'm not really, betting on that. But if it does happen, I will be going to meet other experts and continue on my research, as well as developing the app Astrios, of which the website is going to be coming up soon, with a lot of information and all of the episodes inside, as well as video tutorials, and hopefully a forum where you guys can actually ask questions, maybe ask for some features. If you're unsure about something, you can get in touch, etc. So thank you very much for your time. Although this, I would have preferred kind of being there, kind of to, because last time I had to leave for the airport. I wish I would have been there this time, but I'm sure there might be some opportunities later down the track. And thank you very much.